Okay, so I posted. Oh, a couple of things. So I posted what was supposed to be exam 3 to the assignments folder in Blackboard. You should be able to see that document, print that out, scribble in the places, answer those questions, and then submit it back. And I think I set the deadline to be middle of next week. We can go back and check about that. If
And you put it as Monday.
okay, I'll push that to Wednesday.
Sweet.
Thank you.
If you cannot see that document, exam 3, let me know, and I will get you a copy of it. Now, because this requires handwritten answers, find some creative way of getting that back to me. There is a submission link for the completed document in Blackboard. That could be that you filled it out, that you printed it out on paper, and then you just simply took photographs of your completed document and then submitted those photos. You could turn it back into a PDF. If you have the technology that you can scribble on a document and then save that as a new PDF, either way, let me know if you are not capable of turning it in. Go ahead. What was that? There is an app that what? Okay. Yeah. Thank you.
Let me find it real quick. I have it on my phone. It's free. It's called Tiny Scanner, and it'll convert your pictures into scanned document.
Okay. If if you just want to write that down in the chat so that it's locked in for all of posterity, go ahead and do that for me, please. Okay, the other thing that I did is I put another link and a chapter reading assignment onto your calendar. Because we've lost 3 full days, actually 4, we're not going to do all the little detail. So Wednesday we looked at esters and hydrolysis of esters. At this point I would normally look at amides and do the hydrolysis of an amide. It's the same thing. It's just the same thing. There's a slight twist on it when you do it in base versus when you do it in acid. But in acid, it's the same mechanism. And then what I would do would be to take those straight chain molecules and turn them into rings. And when you put them into rings, of course, half of the room panics and says, this reaction that I've been capable of doing for the past 2 weeks, I am now incapable of because the ring is intimidating me. Cyclic esters are called lactones, and cyclic amides are called lactams. It's in the notes. It's one of the things that we're going to skip over. That would be like an extra detail that we're just not going to cover this term because we don't have time for it. Moving on to the next set of topics, we're going to do something similar. We're going to look next at reaction, the really difficult part. This is the difficult part of organic chemistry 2, where reactions are going to occur at a place that is not the functional group. And if I were in class and we had that week back, I would probably spend 2, maybe 3 days. It's not unreasonable to spend 3 days doing this next one reaction. This time around, we're going to just try and hit it and expose you to this information to the point where you can recognize that it's there and then move on. Because the biomolecules that come at the end of the term are going to take precedence over, those are going to be things that you need moving forward. Okay, you got a lot more, most of you have a lot more biology ahead of you, and you know, a day or two of talking about biomolecules is going to be worth more than an extra day talking about an aldol addition versus a condensation. So with that in mind, we are going to look at reactions now where it's not the functional group that gets to react with the new reactant. And this shouldn't be too much of a surprise, because we're going to go back and it's based in something that we saw much, much earlier on. This is an aldehyde. In fact, what I'm going to do is I'm going to make this be a ketone. All right. So here's a ketone. You know what? Because I make this stuff up as I'm going, I'm going to go back and do this historically the way that we learned it. We learned this as, oh, this is an unexpected way to make a ketone. So I'm going to go back and do it that way. Here we go. If I have an alkene, hopefully you can see that. Is that visible enough for you? Let me see if I can move that a bit closer. Here I have an alkene. If I place that alkene into water with a catalytic amount of acid, what do I make? Alkene plus water in the presence of a catalytic amount of acid.
An alkane.
Ane? No, if I wanted this to turn out to be an alkane, that would mean adding an additional 2 hydrogens. So I would do that as a hydrogenation. Okay, let's go back a little bit. What reaction is it that we learned that alkenes undergo? If my reactant is an alkene, what is my probable mechanism of reaction?
In addition?
Yeah, I was just going to write all the possible answers out. It could be a substitution, it could be an addition, it could be an elimination. I'm going to do an electrophilic addition. And if I add, I'm going to need the acid, to spark that pi bond to be open. If I take an alkene and I put it in the catalytic acid with water, I'm going to make an alcohol. Ring a bell? It should do. Should be familiar. What if I tried the same electrophilic addition of water across a pi bond, only this time my reactant was not an alkene, it was an alkyne. What's my product? Look what I've done. You take the H and the OH and you split them and you put them on neighboring carbons. You put them on vicinal carbons. Alkyne plus water in the presence of acid makes what? Nobody?
Does it make a geminal diol?
We want it to make a geminal diol. We would love it to make a geminal diol. But unfortunately, halfway to making that geminal diol that you want to make, I mean, that's a really good guess. Halfway after the first step, I make this, right? So I've added an H and an OH, and now Markovnikov's rule says, oh, if you're going to add another set of groups across this remaining double bond, then the electrophile goes to that carbon and the nucleophile goes to this carbon, and you would make the diol here be geminal. That's what we would, I think that's what the original reaction was intended to do. However, it goes wrong, because this molecule is part alkene, part alcohol. That's an enol. And enols are famous for doing something. What are enols famous for doing? Enols rearrange. What do they rearrange into? Enols rearrange into ketones, and the equilibrium, and it is an equilibrium, between the enol form and the keto form in this keto-enol tautomerism is very heavily weighted towards the ketone, which tells us something about ketones that we had not considered up to this point. It tells us actually something very important. Okay, first of all, does anybody remember anything about this at all? I'm hoping you do. My next question is going to look for a one-word answer. And that one-word answer is an adjective. It's a descriptive word that describes behavior. Let's look. I have an enol. I have a ketone. These two are in equilibrium with one another. What I actually do is I lose the hydrogen from this oxygen and have it migrate over to this carbon, which pushes the pi component up to here. Okay. The hydrogen that is currently circled in pink is attached to the carbon in the ketone some of the time, because when I look in my other form at that carbon, that hydrogen is missing. It's not here. So I'm looking for a one-word answer. A one-word answer that describes the behavior of that hydrogen.
Does it start with an R?
No, it doesn't start with an R.
Is it catalytic?
I guarantee it's a word you've all heard before. So we've already had one guess. It does not start with an R, and it is not catalytic.
Is it stable? Is there an E?
It is not stable, and there is no E.
Is there an O?
There is no O.
What about an A?
There is an A.
Is there a C?
There are two C's.
It's acidic.
That hydrogen is attached to the molecule some of the time. Some of the time. It's not there all of the time. It's there some of the time. That makes that hydrogen acidic, which is something that we had not considered before. So, when I look at a ketone, here's a ketone, here's 2-butanone. My eyes immediately drawn to, well, that's a pi bond. Oh, look, that bond is polar. Plus, I have lots of electron density on the oxygen because I have lone pairs of electrons. So my eye is drawn to the functional group in the molecule, pretty much prejudicing me to say that's where the reaction is going to occur. Completely overlooking the fact that those hydrogens are acidic and that the reaction could be occurring here instead. That's what we're going to start to see today. Okay? So, we're going to need a name for this. Here's a ketone. It's a long one. This is 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons long. And it's a ketone. So that's octanone. And the ketone is at number 2. So that is 2-octanone. If I want to know where the functional group is, well, that's pretty obvious. The functional group is at position number 2. That's where the carbonyl is. It's where the pi bond is. It's where the lone pairs of electrons are. But I also have acidic hydrogens vicinal to that carbonyl. And that's position number 1, and this is position number 3. So I'm not going to be using numbers to describe that behavior because the numbers are going to change for every molecule that I see. So I'm going to give the positions in this molecule titles. That's the functional group. If I'm 1 position away from the functional group, I am alpha to that functional group. If I am 2 positions away from the functional group, I am beta to that functional group. What's 3 positions away?
Gamma.
Gamma. And then
Delta.
yeah, and then it gets a bit fuzzy, right? How many letters are in the Greek alphabet? Anybody know? Got your alpha, beta, gamma, delta, epsilon, and then it gets a kind of little bit, there's a lambda in there.
24.
Yeah, it's less than in the English alphabet. 24 sounds right. What if my molecule is 34 carbons long? I guess I ran out of positions. You're not going to need much beyond these first handful. But if this molecule just keeps going and going and going, what I'm going to do is I'm going to give up naming the stuff that's in the middle, because the stuff that's in the middle is not important. The stuff that's close to the functional group is important. And then, curiously, the stuff that's way, way, way at the end of the chain is also interesting. What is the last letter in the Greek alphabet?
Omega?
Omega is the last. Very good. Omega is the last letter in the Greek alphabet, and it looks like our W. These are all lowercase. The uppercase omega looks like a horseshoe. So, if I have a long chain alpha. Oh, look, I have two alphas. I have alphas on both sides. See that? Because the alpha tells me I'm one position away from the functional group. That's all it tells me. It doesn't care about what the structure looks like. It just wants to know position. Okay, so we got two alphas, beta and a gamma, and then an omega. And then we start counting back from omegas and giving them numbers. So there'll be omega 2, omega 3, omega 4, omega 5, omega 6, counting backwards from the tail end of the chain. Anybody read your food labels? What type of fatty acid are we told should be in our diet?
Isn't it omega fatty acids? Omega-3s.
Omega-3s, yeah. So find the end of the chain and then count back. And when you reach that number, that's where you put a double bond. The omega-3 means find the end of the chain, count 3 carbons back from it, put a double bond at that point. Those are the fatty acids that you find in fish oil, and apparently they're very good for your heart. But what this reveals is that I have some acidity going on here right next to the carbonyl. All right, if I've got acids in a molecule, I'm probably going to have to rank them. So let's look at just how acidic we might be talking here. Ooh, this is a molecule. It's got a little bit of everything going on. I've got a carbonyl. I've got a carbonyl. I've got a position that is alpha to one carbonyl. I have a position that is alpha to 2 carbonyls. And then I have a hydrogen that I recognize as being part of this bigger functional group that's a carboxylic acid. So I have multiple different types of hydrogens going on in here. And then at this end, I've just got, those hydrogens are just regular alkyls. Okay, I have no suspicion that those would be acidic at all. So if I look at what's going on here.
Which ones did you say you wouldn't be suspicious about being acidic?
CH3, CH2, regular methyls and methylenes, regular alkyl hydrogens in a chain that is not close to the functional group. Those are the bonds that we have completely ignored up to this point and said, you don't break a carbon-carbon bond, you don't break a carbon-hydrogen bond in our reactions unless it's involved in a functional group somewhere where we're told that we can go take it. Okay. So I'm going to rank these in order of acidity. What acidity scale do you think I'm going to use? going to put numbers to this. What numbers do I use?
The pKa.
It's pKa, yeah. Yeah, I'm going to use a pKa scale. Now, on the pKa scale, if I'm looking for an acid, do I want the number to be a big number or a little number?
Wouldn't it be a big number?
Ka would be a big number, but pKa is the negative log of the Ka. So as my pKa values get smaller, that indicates to me that that particular hydrogen is getting more and more acidic. So low numbers mean more acidic. Okay? Do we know what the pKa of a carboxylic acid is? Might have mentioned it. Might have mentioned it. They're all around 4 point something. 4.5, 4.8. So it's not unreasonable to think that the acid part of a carboxylic acid has a pKa of 5. That's about right. A hydrogen right here that is alpha to a carbonyl has a pKa of 16. Now these numbers on their own don't, they don't mean an awful lot. They don't make an awful lot of sense. It's why if you want to talk about pKa's, you really need a table. You need a table, and there is a pKa table on Blackboard. It's been built into Blackboard since the very first day of class. That outlines what all the available possibilities of pKa could be for all of my molecules. And so you can kind of put a sense of this type of structure is this much acidic. And when I look at just a regular hydrogen attached to a regular carbon that's also attached to another regular carbon, I'm looking at a pKa in the mid-40s. So this type of hydrogen is of no interest to acids or bases at all, right? It's not doing anything. That's a low number. So this one is the most acidic. Hopefully, obviously, that's the most acidic because it's part of the molecule that contains the word acid. This is a carboxylic acid right here. So that should be the most acidic. That's a number that's 16. If my hydrogens find themselves between 2 carbonyls, that pKa is now 9. Here's how we put this into some kind of frame of reference. This is ethanol. It's an alcohol. It has a hydrogen that is directly attached to a highly electronegative atom. It is not unreasonable for us to think that that bond between the oxygen and the hydrogen can be broken. We should be thinking about alcohols as being slightly acidic. What's the pKa of an alcohol?
16.
It's 16. So what we're saying is just being next to a carbonyl makes the hydrogens on that carbon the same level of acidity as if they were an alcohol. That's pretty profound. Okay? So we cannot overlook the fact that I've got this molecule. I think it's pretty obvious that the first this reaction site right here is the most reactive, and that should go first. And then I should be thinking about those carbonyls doing something or other, but I cannot overlook the hidden fact up to this point that those acidic hydrogens can be taken. And if they can be taken, then we should do it. We should go take them. If a molecule that contains a carbonyl has alpha hydrogens, those alpha hydrogens can be removed. And if I can remove them, I can probably replace them. So let's do that. Here's a molecule. Oh, what's its name? Propanal. I have 3 carbons. I have a carbonyl. That carbonyl is an aldehyde. Oh, a little bit off screen here. That is propanal. Propanal has some things going for it and other things not going for it. Okay, first of all, has a pi bond, has lone pairs of electrons, can do the reactions that we're expecting aldehydes to do. What reactions are we expecting aldehydes to do?
They can turn into an acetal.
Okay, that's absolutely possible. What was the name of the mechanism when we turned an aldehyde into an acetal? Was it an elimination, a substitution, an addition? Was it a nucleophilic addition, an electrophilic addition, a nucleophilic substitution, an
I
electrophilic?
think it was a nucleophilic addition.
So nucleophilic addition. Aldehydes react by addition with nucleophiles, and they react by addition, not substitution, because there is
Double bonds.
no leaving group. So aldehydes have a carbonyl that's experiencing electron withdrawal here at the carbon, means it wants to react with nucleophiles here at the carbon. But there is no leaving group. So this is going to be a nucleophilic addition. All of that's still true. You should expect this molecule to undergo nucleophilic addition with nucleophiles. It will. But it's going to do something else as well. Because now that we've primed our eyes to look for it, This molecule contains alpha hydrogens. And those alpha hydrogens are slightly acidic, which means they can be removed. If I can remove them, maybe I can replace them. If I take this aldehyde and I place it with bromine, Br2. We've seen bromine before. We saw it pretty early on in Organic 1. It is a homonuclear diatomic molecule. 2 atoms of bromine stuck together. And remember, one of the keys to success for oxygen chemistry is that pi bond doesn't want to open with something as weak as a bromine. Go ahead and protonate that oxygen to make it want to open. If I do that, I get this. I replace one of the alpha hydrogens with a halogen. And I've turned my propanal into 2 bromo propanal. This reaction is an acid catalyzed alpha monohalogenation of a ketone or an aldehyde. I get to put 1 halogen in, just the 1. And then you realize, why on earth would he do that? Didn't you just tell me that the alpha hydrogens were acidic? Alpha hydrogens are acidic. So why did we do our reaction in acid? Shouldn't we have done it in base? Let's go ahead and do it in base. If you do the same reaction in base, all the alpha hydrogens get replaced. And for reasons that will never be explained, reactions are catalyzed by acid, but are not catalyzed by base. They are promoted by base. Don't know why. This now is a base promoted alpha per halogenation. Per means all of them.
What is the difference between promoted and catalyzed?
Don't know. I'm not going to tell you. For some reason, we call reactions that are catalyzed by acid catalyzed, but we refuse to use the same word for reactions that require base. Probably because the base isn't the base isn't regenerated at the end, is probably what it is. It's not truly catalytic. So reactions are base promoted or acid catalyzed, because you get the acid back at the end. Mono in acid, we're going to replace one of them. Per halogenation in base, we're going to replace all of them. All of them. Now you can do this with chlorine or bromine or iodine. It's easier. Chlorine's a gas. Chlorine is a poisonous gas. So we don't typically want to use that. But we could. Bromine is a liquid. It's really dangerous. It gives you incredibly bad chemical burns. And iodine is a solid that's soluble and is not dangerous at all. In fact, it's antiseptic. So there's some wiggle room right here. Let's look at what the difference is between some ketones would be. Oops. One, two, three, four. Butanone on the top, cyclopentanone on the bottom. A halogenation in acid, a halogenation in base. A halogenation in acid, a halogenation in base. You have everything you need to know to draw me the 4 products. Go ahead and do that. Draw me what the 4 products are. In these reactions, the carbon framework remains intact. The carbonyl remains intact. Our reactions have occurred somewhere other than the functional group. Okay, for the top one, how many chlorines am I expecting?
One chlorine? One.
1. Where does it go?
At the alpha.
I have 2 alphas. Which one?
The one on the right.
Is the best answer. best answer. Remember, we looked earlier on at enols, and if I converted my ketone to be in its enol form, having the double bond in the middle is better than having the double bond at the end. So putting my halogen in the middle is better than putting it at the end. Okay, for this one, how many halogens make it into the product?
Both.
How many total halogens? How many chlorines?
2 chlorines.
Perhalogenation means everything. All the hydrogens on that methyl got replaced, and all the hydrogens on this methylene got replaced. 5 chlorines made it into the product. Okay, what about this one? Now it's a ring, but it's not more difficult than your previous question. If you're intimidated by the ring, put your thumb over the ring, and now it's just a ketone. How many chlorines in my product?
1.
This side and that side, the same as each other, so it doesn't matter which side you put it on. Okay, if I did this in base, what do I get?
You get 4 chlorines, 2 on each side.
There you go, very good. Okay, what we're going to do Monday is difficult. I'm going to add carbons to the alpha positions. And the carbons that I'm going to add might be molecules of reactants. So I'm going to find a reactant. I'm going to find a place in that reactant that will add to the alpha position. And then my other reactant is going to be a same molecule. This is going to be difficult. I'm going to give you the 2 buzzwords, and I want you to, plus I'll put this on the calendar. The reactions that we're going to do on Monday are called the aldol and the Claisen. These typically are the things that students find the most difficult in the entire semester. Okay? If at this point we've been coasting by just allowing the class to come to us, perhaps for the next lecture we get ahead of this. You watch the videos from the previous year, you read the notes, and we get a little bit ahead of this, because this can be as difficult and as big and as ugly as we want to make it. In its simplest sense, it's small and we can contain it, but it can just spiral out of control, because the product of the aldol, which is now a conglomeration of molecules stuck together, can also be a reactant in another aldol. Okay? If there's ever a time to read ahead, watch ahead. It's for what's coming on Monday. All right, have a great weekend. Stay safe. Don't go outdoors. All the other usual stuff. And we'll see you Monday.
Sweet joy.